Just as sound waves propagate in water, it was once believed that light waves propagate in a medium called ether. This presented an opportunity for experimental physicists to measure the motion of the Earth with respect to the ether. In 1887, two scientists named Michelson and Morley conducted an experiment to do just that. But no matter which direction they pointed their apparatus, they measured the same speed of light through the ether. This forced them to conclude that the ether did not exist, and that light would always be seen traveling at the same speed. This puzzled scientists worldwide. Well, except for one, Einstein. Einstein imagined what it would be like to see the universe from the perspective of a beam of light. He asked questions like, how would a photon perceive the passage of time? And will distances shrink and stretch depending on the motion of an observer? Of relevance to him was the fact that experiments had proven that light waves were special compared to sound waves or water waves, in that they didn't require a medium through which to propagate. In helping us to understand these new revelations, Einstein had to tackle problems which few could ever even consider. In one of Einstein's most famous papers, entitled On the Electrodynamics of Moving Bodies, he introduced two very important ideas. Ideas which are now among the foundation of modern physics. They are, 1. The laws of physics are the same in all inertial frames of reference. And 2. Light moves at the same speed relative to all observers. That first postulate seems reasonable. The laws of physics are the same for me here as they are for you sitting there. The laws of physics are the same on the moon as they are here on Earth. In physics, this principle is essential, as we use it all the time in order to learn about places that are distant from us. An inertial reference frame is either an experiment at rest or one moving with a constant velocity. Inertial frames are not accelerating. For example, someone standing in a high-speed train would experience the same laws of physics as someone stationary on the ground, so long as neither are accelerating. The first postulate is intuitive to human beings, which makes the second one impossibly hard to believe at first glance. Einstein's second postulate was that light moves at the same speed relative to all observers. So if we were to measure the speed of light from a fast-moving astronaut, we don't add the astronaut's speed to the speed of light. Weird, right? The speed of light always comes out to the same value, no matter how fast the astronaut is traveling. Einstein realized that if the laws of physics are the same for all observers, then all observers must agree on the value of the speed of light. You've probably experienced some of the strange effects of changing reference frames before. Have you ever been in a parked car when an adjacent car starts moving? In some cases, your brain tricks you into thinking that you're moving instead of the other car. Since motion is relative, we can always choose a reference frame that is stationary, even if there's relative motion to something else. Let me explain. Suppose you're riding in a self-driving car. Some fast cars are passing you in the left lane, and you are passing some slow cars in the right lane. If all the cars are moving at a constant but different speed, each car is their own inertial reference frame. If you observe the cars from the ground, they will all appear to be moving. If, however, you choose a reference frame of the car in the middle lane, the cars on the left appear to be moving forward, while the cars in the right lane appear to be moving backwards. Without the road in the background, we can't figure out how fast the cars are traveling. The only thing we can tell is how fast they're traveling with respect to one another. However, this becomes problematic when light is introduced. Instead of driving during the day, what if our cars are driving at night? They'll need to turn their headlights on. And if the center car turns on their headlights, they'll see photons leaving at the speed of light, c. Let's consider the headlights of the cars in the left lane. Does the speed of light coming from the fast car appear faster due to the relative motion? No. Even though the red car is moving faster, the photons coming out of the headlights always appear to move at the speed of light, c. The speed of light from the middle car is not c minus 10 kilometers due to the motion of the cars. And the same is true for the slower blue car. The speed of light is always measured as c. Weird, huh? Einstein thought so too. Clearly, if Einstein's second postulate, that all observers measure the speed of light as a constant, is to hold true, we need some other kind of transformation group so that every observer can see the light beams moving relative to themselves at c. In order to do such a thing, Einstein realized that our intuitions about space and time must be incorrect, and that a new theory is required to describe how all observers, moving at different speeds, can measure the speed of light to be a constant.